So now our claim is that with an appropriate choice for the divisor B, by the way, you may also have the same observations for the map phi 2. And now our claim is that for an appropriate choice of this divisor B, we want to see that the image of the Riemann-Roch space of A1 plus B under phi 1 and the image of the Riemann-Roch space of A2 plus B under phi 2 has non-trivial intersection. So first, it is not so clean why we want to see this claim, because if we are able to see that, if we are able to prove this claim is true, then if the claim holds, then that means we can choose an element which lies in these both images, or equivalently, we can choose functions from the Riemann-Roch space of A1 plus B and the function x2 in the Riemann-Roch space of A2 plus B, such that x1 times omega 1, the Weyl differential x1 omega 1, x2 omega 2 has the same non-zero value. And if this is true, then we can write omega 2 as x1 times x2 inverse times omega 1. And indeed, this shows us the existence of the non-zero function set. And more explicitly, this shows us the omega 1 forms a basis in the Weyl differentials over the function field f. So now our purpose is to see that this claim is true. And in order to prove that, again, we need to use a statement or an observation from linear algebra. Which tells us for given subspaces U1, U2 of the finite dimensional vector space V, its dimension, the dimension of the intersection of these subspaces is bounded below the dimension of each subspace U1 and U2 minus the dimension of the ambient space where they live in. So this statement in this is true because we can verify it easily. Since U1 and U2 is a subspace of V, U1 plus U2 is also a subspace of V. The sum also lies in the ambient space. So that means the dimension of V is always bigger than or equal to the dimension of U1 plus U2. And if we recall the rank nullity theorem from the linear algebra, we can compute the dimension of sum of two vector spaces as the dimension of each vector space minus the intersection of the subspaces. And indeed, if we replace in this inequality, if we replace the position of dimension V and the dimension U1 and U1 intersection U2, we can verify these statements. Now our claims that we want to see. So if we replace this U1 by by this vector space, this is going to be dimension of the divisor A1 plus B because of the injectivity of phi 1. And similarly, if you replace U2 by this vector space, and if you are able to see that its dimension is bigger than or equal to 1, we can say that that means that the intersection is not trivial space. So more explicitly, if we use the notions from the function field, so that means if we let this divisor be as positive and its degree is large enough, because we want to apply the Riemann's theorem, we want to see that first the dimension of the Riemann row spaces can be computed in terms of its degree explicitly. So that means dimension of AI plus B is equal to the degree plus 1 minus G. And as I mentioned before, if in this setting, if we set U1 as the image of the Riemann row space A1 plus B under phi 1, or similarly for U2 and phi 2, these are injective, so the image is going to have the same dimension of the Riemann row space. Indeed, these vector spaces lies in the Weyl differentials of the divisor minus B, and this minus B will be considered as V in this observation. So, and we also know that it has dimension. Its dimension indeed can be computed in terms of index of specialty of the divisor minus B. Which is exactly degree B plus G minus 1. So that means the dimensions of these UIs, or the dimensions of this vector space, is less than or equal to degree B plus G minus 1 for each I. And now if we apply our observation from linear algebra in with respect to this notation, we can see that dimension of U1 plus dimension of U2 minus the dimension of the ambient space where they live in this case, this is going to be dimension of the space of Weyl differentials of the divisor minus B, less than or equal to dimension of this intersection. So to see that this intersection is not trivial, is a non-trivial vector space, it will be enough to compute the dimension on the left-hand side, and that the dimension of U1, since we choose the divisor B with sufficient large degree, which allows us to compute these dimensions U1 and U2. So that means dimension of U1 will be degree of A1 plus B plus 1 minus G, and similarly dimension of U2, degree of A2 plus B plus 1 minus G, and minus the dimension of the space of Weyl differentials of the divisor minus B can be computed as the degree B plus, so degree B, yes, we have 2 degree B minus degree B plus degree A1 plus degree A2 plus 3 times 1 minus G. And here note that this quantity is independent from the degree of B, particularly independent from the divisor B. So that means its degree also independent from the degree of B. And if the degree B is large enough, we can see that this is, with this particular choice of B, this dimension is going to be strictly positive. And this shows us so that means B is positive and the degree is supposed as sufficiently large. We can see that the dimension of this intersection is strictly positive, in that this is not a trivial space, and this completes the proof of the claim, and consequently our proof. So so far, indeed, we considered Weyl differentials for given divisor A. So we consider, first we give the divisor A, and we consider the Weyl differentials, which are vanishing on the other space of A plus F. And now we want to understand, we want to first fix a Weyl differential and another Weyl differential, and we want to understand which divisors, for which divisors its other space plus F lies in the kernel of this another Weyl differential. So that means in some sense we want to attach a divisor to each another Weyl differential. And for this purpose, for a given another Weyl differential, we will consider the set of the divisors such that this another differential vanishes on their other spaces plus F. And indeed, okay, the main motivation of this introducing this notion will be to see that indeed we have a divisor that's going to be in some sense maximal with respect to partial on the divisor group, such that this particular Weyl differential vanishes on this maximal divisor, let me call it omega, and it won't vanish for any divisor which is bigger than or equal to for this divisor. So more explicitly, what I want to say, our first motivation, our first purpose will be to see that if we consider all divisors such that this given non-zero Weyl differential vanishes on their other space plus F, then there exists uniquely determined divisor omega such that for any divisor in M of A, we have is less than or equal to omega. So that means this divisor omega gives us, in some sense, the upper bound, the maximum divisor of this set.